This is Big History to 2020, number 6. Today we are looking at cosmic microwave background. This is a picture of the background. In this particular picture, two things has been removed. The first is the effect of our galaxy, the Milky Way. The second is the two poles of our Earth, which generate quite a bit of noises. So they are removed, and this is the resulting view of the sky in the microwave region at around 2.75 degrees Kelvin. The red dots there and the blue dots there represents about 0.0002 degrees deviation from the average. I repeat, the number is 0.0002 degrees from the average. So here is the summary. The average temperature is 2.725 Kelvin. That is the temperature above absolute zero. And the cold and warm regions differ by 0.0002 degrees. And it is a Mulvaney projection. A Mulvaney projection means the area represent equal areas. Now this cosmic microwave background is a faint cosmic background radiating, filling all space. The important thing here is all space. Now, if we look at our night sky using an optical telescope, we will find that there are some places where we have a dot of light, or a star, or a galaxy, and so forth. But most of the space in between them is dark. But this microwave background comes from every direction, including those areas which looks dark in the optical telescope. No matter how sensitive your radio telescope is, this faint noise is always there. So it's almost isotropic. That means it is everywhere. Before we look into what is this, let's understand how something can emit light. Last time we talked about atomic spectrum, when the electrons around the nucleus of an atom get excited. That means it absorbs some light. Then you will jump from one of the orbit into another orbit. When the electrons go back to its fundamental state, jump back to its original state, it will emit some light. And that light is very typical of the particular atom. And therefore, different elements will have a different atomic spectrum, represented at lines of different colors. But there's another way of emitting light that's called black body. A black body means it absorbs all light. Now, in our visible region, a black body means it absorbs all light and it doesn't reflect anything. But we have to remember that a black body not necessarily do not emit radiations. The radiation emissions is actually at a different range that our eye can't see. When a black body, that means something which absorbs different kinds of light. Here will include light in the infrared region as well as ultraviolet region and so forth. When we have a black body, it absorbs radiation from around it. But if it is in thermal equilibrium with the surrounding, that means its temperature is the same as the surrounding temperature. That means the energy it is absorbing from light must somehow get emitted, otherwise its temperature will rise. So when it is in thermal equilibrium, that means it's in the same temperature around with the surrounding. It must be also emitting energy. That emission is called black body radiation. Here is a diagram. On the left, we have a visible spectrum photo. That means this is the color our eyes can see. On the right, it is taken by an infrared camera. The color there is artificial color being added to it by the software. So you can assign different color to different temperatures or different radiations. And this is the infrared. When it is in equilibrium, as shown in this case, then it should be something like the brown. But we know our body is at a higher temperature than the surrounding, and therefore we will see some brighter yellow temperatures, which represent higher temperature than the surrounding. So we know that these radiations from the black body is dependent on its temperature, and that has been well known for a long, long time. So this is the expected spectrum from a black body at a different temperature. At around 300 degree Kelvin, it will be reddish. As it is rising temperature, it will become white hot and eventually becomes even blue. Our sun is at around 5,000 degrees Kelvin. This is the 5,000 degree looked at here. The blacksmith have been using this technique to estimate the temperature of the metal they are heating up. If it is dull red, as shown on the very left of this color chart, it is around 1,000 degrees. When it is white hot, then it will be almost middle, which is 6,500 degrees. So this color chart actually represents what our eye will see from a black body. The black body equation, which the spectrum, the shape of the curve, was a physics puzzle for a long time until Planck used his photon theory, and then we come up with a proper equation. And eventually Einstein built on that and talk about the electromagnetism, electromagnetic radiation, and so forth. Okay, let's go back to this cosmic microwave background. We will talk about the discovery now. In 1964, there are two engineers working at Bell Labs. They want to measure to detect the radio waves bounce back from a echo balloon satellite. That means they want to send up a satellite into the atmosphere and then use a radio wave to detect the balloon and then get the signal back. So in order to measure these very small radio waves bouncing back, they must eliminate all possible interference and noise from the receiver. So they try to cool the receiver to the lowest temperature they can get, which is 4 degrees above absolute zero using liquid helium. And they also try to clean out everything. They repeat it again and again, and they are always picking up a radio signal in the microwave region. They can't avoid this noise. This noise is about 100 times more intense than they have expected. So it must be coming from somewhere. It is there, date and light pointing in all directions is always there at around 7.35 centimeters. Since it's coming from everywhere, so they figure it must not come from Earth, the Sun, or our galaxy. They check their equipment. We even remove the pigeons nesting and the pool, etc. But it remains there. So they concluded that it must be coming outside from our galaxy. Uh, why they say it is outside our galaxy? Because we know that if you look at the night sky, there is a patch of light called the Milky Way, which shows many tiny little lights in a band. That is our own galaxy. So if the signal is coming from every direction, so it must be there for a long time. It must be coming out from outside of our own galaxy. If it is coming from a galaxy, then when they point the antenna towards our galaxy, they should pick up a stronger noise, a stronger signal. But it's not. It's the signal is all the same around the light sky. So it must be coming from outside of our own galaxy. Now that's part of the problem. The problem is now we have some engineers who were trying to do some work, detect some microwave, and they pick up a noise which they cannot explain. So that is the experimental part of the issue. On the other side of the equation is the theoretical part. So about 60 kilometers away were some physicists at Princeton University. They figured that if Big Bang really occurred as described last time, then when the universe temperature drops below a certain temperature, then the atoms there will be able to recapture all the electrons and becomes neutral. Once it is neutral, then it becomes transparent. And at that point, there will be the growth, the black body radiation at that particular temperature. So they are trying to figure out if the universe actually go through a Big Bang like the theory described, they should be able to detect this afterglow when the universe becomes transparent. Now, because it is so long ago, so the universe has been expanding, and therefore the wavelength of this uh, light will have been extended from very high in the ultraviolet to the violet region into the nowadays microwave region. So they were expecting to see this microwave background radiation. So on one side, we have people picking up these microwave signals and trying to figure out why. On the other hand, we have some theoretical physicists trying to find this residual growth of the universe. Well, we need somebody to make the link. So another professor at MIT read the paper and they talk about that and link them together. And suddenly they realize that the signal picked up by the Bell's engineers is this afterglow of the universe when it becomes transparent. This is the radiation as a signature of the Big Bang. So they published their results jointly, and eventually both teams got their Nobel Prize for their joint detection. So once again, this is the diagram. So there are a number of things we want to talk about in this particular diagram. First of all, the difference in the microwave is very small. We exaggerated it using color here. Red is just 0.0002 degrees higher than the average. Blue is only 0.0002 degrees lower than the average. So it is a very small temperature difference. The whole universe seemed to have a uniform temperature at that time, but still we detect this minor temperature difference. We need to explain this later on. This cosmic microwave background becomes a landmark evidence of the Big Bang. That particular image, well, we can say, is the earliest image of the we have got from the universe. So these are some of the jargons used to describe this. When the universe was young and before the formation of stars and planets, it was denser and hotter and filled with a uniform glow from a white hot fog of hydrogen plasma. As the universe expanded, both the plasma and the radiation filling it grew cooler and cooler. When the universe is cool enough, then photons and electrons combine to form neutral hydrogen atoms. Without all these charged particles, light is able to pass through. There's no scattering, and therefore the universe becomes transparent. So the photon that existed at the time of this called decoupling will propagate throughout space ever since the beginning of the universe. Okay, ever since this decoupling. These fine details of the cosmic background radiation. After the discovery of this one, people are interested to see whether there is any difference. So a number of experiments have been launched, including Cosmic Background Explorer, COBE, and other like the Boomerang or Daisy, etc., etc. More and more measurements are made, and the image becomes more and more accurate. So it is now to a very high degree of accuracy. So the latest one is actually the the Planck probe. So this will be the last slide. In this slide, we'll see the differences of resolution. The initial one, Kobe, is almost uniform with a little bit difference. That difference is due to the our Milky Way as well as our polar effects. Then we have a little bit higher resolution image from WMAP, and then even higher resolution from Planck. So we are now getting pretty high resolution of the sky. Now, in next time we'll talk about these fine structures, the origin of them, and how they come from, and then we'll later on talk about what is the implication of these small differences in temperature. See you next time.